All right, let's talk about wave phase. Wave phase is kind of a strange idea, but it turns out to be very, very, very useful and not really that difficult once we understand what it means. The word phase is used to describe a specific location within a given cycle of a periodic wave. So when I look at a periodic wave, here I've got two cycles. Now, point A, point B, point C, point D, point E, and so on don't represent the same place within the cycle that goes from A to G. They just don't. So we want to be able to talk about the relationship between A and other parts of another wave, the later cycle, that are kind of the same thing as A. So if it's the same thing, we say that they're in phase. So let's look at this. All right, so we got point A. What other points are in phase with point A? Well, point D is at the same place, but the wave's not doing the same thing. Here the wave's going up, here the wave's going down. So A and D are not in phase. They have different phase, all right? What about, well, it's obvious that B, C, E, and F. What about G? Well, at G, we've got same place, doing same thing. So A and G will be in phase. All right, let's look at point B. Point B is an easy one because it's a peak. Anytime you're at a peak, there's only one place in the wave where you can get to that peak. So any place you're at the peak, you're in phase. Good enough. Obviously, F is not, and it's kind of the opposite. All right, we'll talk about that in a minute. What about point C? Well, for point C, we've got two possibilities, H and J. Now, with H, it's at the same location, but again, it's not doing the same thing. So C and H are not in phase, but C and J are. All right, fairly simple. Trust you understand it. Just look, same place, doing same thing, in phase. All right, so why do we care about this? Well, a wavelength can be defined as the distance between any two consecutive locations that are in phase with each other. So that's kind of nice. It means I don't need a crest and a crest or a trough and a trough. I just need phase, same phase. Done. Wavelength. What if they're out of phase? If they're out of phase, we'll use some trig to describe how far they are out of phase. So just like our standard sine and cosine graphs, we're going to take the whole wave as being 360 degrees. Or if we're using radians, we'll use 2 pi. But let's just go ahead and work in degrees for now. So what about A and B? They're clearly not in phase. So how far out of phase are they? So the question, let me rephrase it, is how far do I need to go inside the wave to go from A to B? All right. Well, the easiest way to look at this is as a fraction of the wavelength, which is really what phase is doing. So the wavelength is all the way from here to here. Now, half the wavelength is that, so this would be a quarter of the wavelength. A quarter of 360 degrees is 90 degrees. So we would say that A and B are 90 degrees out of phase. All right? What about A and C? Well, A and C are crest and trough. Now, in this case, it's a whole half wavelength out of phase. So we would say 180 degrees out of phase. Now, A and C are actually opposites in some sense. So instead of saying 180 degrees out of phase, sometimes people say they are completely out of phase. All right, A and D. Well, here we got to go all the way here, then this whole thing. So we could say 270 degrees out of phase. But we could also say A and E are in phase, and D is just 90 degrees backwards. So we could either say 270 degrees out of phase, or we could say 90 degrees out of phase in the other direction, or negative 90 degrees out of phase. All right, that's phase.